Hello everybody. So this is the third lecture of this series about FR theories of gravity. In the first lecture, we introduced the mathematical structure about the FR theories of gravity, and we derived the modified Einstein equations in Jordan frame, in the original frame, where the curvature of the space-time described by different way from the Albert Einstein form. In the second lecture, we introduced the idea of the conformal transformation, which transformed the action from Jordan frame to Einstein frame, where the gravity where the curvature described again as linear or bilinear function of Ricci scalar, of course, Ricci scalar in Einstein frame. But that's introduced, as we mentioned before, new degrees of freedom, which is seems as a scalar field. Now, in today's lecture, I'm going to talk about the application of the FR theories of the gravity. We will see how we apply this, or what the cosmological, let's say, results when we apply these FR theories of gravity on the whole universe, taking into account the matter in the universe. And at the same time, also see what the benefit of the conformal transformation, because last lecture we only introduced the idea of the conformal transformation. We mentioned that now that will make the calculation easier, but we didn't see this clearly and directly. But today, in today's lecture, we will see this directly. Now, before starting this lecture, let me, as usual, remind you about the main references for the lectures, and especially for this lecture. The first lecture, or the main lecture for this series, is notes on FR theories of gravity by Spuria. And also we have the FR theories of gravity. And today, the first part of the lectures today, I'll take it from this interesting book, An Introduction to Mathematical Cosmology by Islam. It's a really interesting, easy, direct book. It's so suitable for the first course in cosmology. They will introduce the main derivation in the cosmology directly and easily. It's highly recommended to read this book if this is the first time you are dealing with the cosmology. I will use the chapter 3 of this book to review and to give a quick revision about the cosmology in the field of GR, in the field of general relativity. So let's go to the third chapter, and chapter 3. This is chapter 3. And especially I want to go to Einstein equations for Robertson-Walker method. Now, before talking about these Einstein equations, let me introduce the Robertson-Walker metric. Robertson-Walker. Usually it's RWL metric. What's this metric? Now, of course, if you want to describe the distance between any 2 points in the space, you need to use the metric. For example, if we are in the Euclidean space, as you know, that this will be described as ds squared equals dx squared plus dy squared plus dz squared. You know that if these 2 points and you want to take the Cartesian coordinates x, y, and here we have z, then just take the components of this position of this point with respect to this point as differential elements, then use Pythagorean theorem. So this is in, let's say, in Euclidean space. We have only space, not space-time. And in addition to this, we are of course in the flat space-time. Okay, now, as you know, that's in case of Minkowski space. Now, in addition to this, we will add the 4th dimension, which is the time. So now the metric will be negative c squared dt squared plus dx squared plus dy squared plus dz squared. Now let's see what about the universe. We want to find the metric, but for now, for the universe and on large scales, not on small scales. Yes, I shared the screen. So on large scales, how we can do this? The description of the universe depends on something we call it cosmological principles. Cosmological principles state that the universe on the largest scale is homogeneous and isotropic. Of course, on the small scale, it's not homogeneous. We can see that in spot of the space there is the sun and the planets. The other area there is nothing. But on the largest scale, the universe seems perfectly homogeneous with some with perturbations. So we need to build now the metric for the space-time on the large scales to be homogeneous and isotropic. This is the first thing. So this one, of course, homogeneous and isotropic. Now, on the other side, also we need to take the expansion of the universe into account. So we need these spatial coordinates to be expanded. So if we write d squared as negative c squared dt squared, then plus here let's write it as dxi, where I stands for 1, 2, 3, x, y, z. Then here we need to add something to represent the expanding of the universe. This expanding of the universe is represented by at, where at is, of course, here 80 squared for each one of the coordinates. Its scale factor is called scale factor. Now, about that, the universe should be homogeneous and isotropic. Actually, this is not the only possibility. This is one of the possibilities, or this is one of the, let's say, this is one of the geometries which cover the homogeneous and isotropic universe, which is a flat geometry, or we call it a zero curvature geometry. But also there is another possibility. For example, the surface of Earth, the surface of sphere. Let's imagine that we are talking about two-dimensional space. So, and we looked at the surface of the sphere. I'm not talking about the sphere itself, the surface of the sphere. Actually, the surface of the sphere, it's homogeneous and isotropic. It doesn't differ between one. Look, about the homogeneous, we are talking about the matter. But about the isotropic, it seems that it's isotropic. If we looked anywhere and everywhere around this, on the surface of this sphere, the space will be identical. So this one is called, in the terminology of the geometry, it has positive curvature. Positive curvature. Example about it, the sphere, the surface of the sphere. Now also there is another thing, that's geometry with negative curvature. And the negative curvature, it seems like we have, that's the saddle. See the saddle. I prepared here something. I think it will be helpful. Yeah, this one. So this is the first geometry, which is called zero curvature. Plane surface has zero curvature. For flat space, if the plane is taken and the triangle constructed by pointing. So in the flat space or in zero curvature, if we draw the triangle, we will find the usual result that we have a triangle, and the triangle, the sum of the angles of the triangle is equal pi, or 180. And if we draw any two parallel lines, they will still parallel to each other, to themselves, and they will never meet with themselves. Now, on the other hand, we have this positive curvature case. And positive curvature case, example about the surface of sphere. Now, if we draw a triangle on the surface of sphere, we have that the sum of these angles will be larger than 180, larger than pi. And at the same time, if we draw two parallel lines, they will meet at some point. It's similar way if you draw two parallel lines on the Earth, they will meet at some point. Now, so this is called the positive curvature case. The negative curvature case is like this one, like the saddle. It seems like the saddle, but let me just be sure about the name of this. So this is negative. Yes, saddle shaped surface. And this one, if we draw a triangle on this one, the sum of the angles of the triangle will be less than 180. And if we draw any two parallel lines, will be divergent from each other. So this is different geometries, and all of them, they describe homogeneous and isotropic universe. So on the larger scales, we cannot say that the universe is has positive, negative, or flat, or zero curvature geometry by prediction or theoretically. The observation will support one of these, curvature, and until now, the observation support the flat or zero curvature that I'm talking about the whole universe. But anyway, when we build the metric, we need to take the three cases into account. Now, let me review here quickly that, let's back the book of Islam. That's if we want, let's see, if we want to write this metric, in case of spherical coordinates, so that will be a squared t, and here we have dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So that will be this if we use the spherical coordinates. This is the metric will be. Now to enter the other possibility, so here to enter the other possibility for the metric in general will take the following form. So this is the derivation. Yeah, this one. We'll take this form. Now let's look here. It's that we have this K. K that stands for representing the curvature case. So let's K, if K equals 0, if we took here as K equals 0, then this term will be cancelled, and we can see that this is the spherical coordinates which represent the surface of sphere. Now if we took K equals positive 1, so this is for positive curvature, and that's will represent the coordinates on the surface of sphere. I'm sorry, here maybe I said the coordinates on for K0 represent the flats, the Euclidean, let's say for the spatial part without the expansion, the Euclidean space. Now for K equals 1, this is represent the surface of hypersphere because the surface described by 3 dimensions. Usually the surface of the usual sphere will be 2 dimensions. But now the surface of this sphere is 3 dimensions. We cannot imagine this one, imagine this one. Why? Because if you want to imagine it, remember that the sphere, where the surface of the sphere is 2 dimensions, while the sphere, all the sphere exists in the 3 dimensions, 3 spatial dimensions. Now, if you want to imagine the 3 dimension, the three dimension, if you want to imagine the sphere with 3-dimension surface, then this sphere, the whole sphere, will exist in 4 spatial dimensions. And we cannot imagine these 4 dimensions or 4-dimensional sphere because our brain and our sense, they are constrained in 3 dimensional space. Okay, so we can take it as mathematical concept here. Now for k equals 1, that will represent the negative curvature. Classically, or in 2 dimensions, it seems like the saddle shape. So here, this is about the k. K will represent these 3 possibilities. As I mentioned, until now, the most possibility, or the highest possibility, that the universe has the flat structure, spatial structure, and zero curvature structure. Okay. Now, okay, so what's the point here? The point now we have here, we describe the metric. We can see that the metric is homogeneous and isotropic. It's expanding because here we have this R. This R, by the way, it's A. Usually we call scale factor, we give it, most of the references, they give it the symbol A, but here in this reference, they give it the symbol R, because they used A for another thing. Okay, so now, as you know, that's usually this metric represented by the metric tensor as following: G mu nu, dx nu, dx nu. And for example, for Minkowski space, G mu nu will be negative 1, 1, 1, 1. For Euclidean space, 0 will be 1, 1, 1, etc. But now for the general case, to take this form. Now we can, by comparing this one by this one, we can conclude what's the components of G mu nu, where, for example, G00 will be C squared, G11 will be this, G22 will be this with this, G33 will be this with this, because this is represent dx1, dx1, dx2, dx2, dx3, dx3. We can see that there is no dx1, dx2, dx2, dx3. So the only radial components exist, and the other components are vanishing. So here the components, we can find that the components as following. This is G011. 1, it means that now we are talking, we took that C equals 1. G11 will take this form, G22, G33, and this is the inverse geometry, the inverse metric. Of course, we depend on concluding this one, that G mu nu up and down, that will be equal to 1. So we can derive these equations. And now when we have the components of this is what's important. Now we have the components. So we have here the components of G mu nu. So G mu nu now, it's none. We know what G mu nu, we know what the components of G mu nu. Now let's remember Einstein equations. Einstein equation says that R mu nu minus 1 over 2 G mu nu R equals 8 pi G T mu. Now let's look at the left side. Left side say that you have R mu nu, you have R, and R is G mu nu, R mu nu. R mu nu contains gamma mu nu sigma, and gamma mu nu sigma contains, and the derivatives, I think. And the gamma mu nu sigma, yes, there is a derivative of gamma mu nu sigma. And gamma mu nu sigma contains G mu nu and the covariant derivatives of G mu nu. So now if we define the components of G mu nu, easily we can find Christoffel symbols. Directly we can find Ricci tensor. Then we can find Ricci scalar. So the left-hand side, by knowing the curvature, the metric tensor, we can define and find the form of the left-hand side of Einstein equations. By doing this, we can find the non-zero components of so we can find the non, just 1 second, please. Okay, so now as I mentioned, that's now we have G mu nu. We have the components of G mu nu, so we can find the non-zero components of crystal symbols, and these are the non-zero components. It's long. It's not long actually. It's direct conclusion, and you can find it. Sorry, I think I forget to share the screen. Okay, so again, here we have the components now of G mu nu. So directly we can find the components of crystal symbols because it just contains the metric tensor and the covariant derivatives of the metric tensor. And all here the components of the metric tensor, they are depending on the time. So that will make the things easier, and that's you'll find that many terms they will be cancelled directly and immediately. Okay, then we can find the non-zero components of Ricci tensor R00, R1, R22, R33, and finally you can find the Ricci scalar, where the Ricci scalar is G mu nu, R mu nu, and we'll take these. Now, what about the right-hand side? Because let's remember that Einstein equations say that G mu nu, and now this side is none, and here we have 8 by G T mu nu. So what about this side here? How we can describe this side? And by the way, when I say that this side described, now we will see what the meaning of this. So T mu nu, the matter in the universe, the whole matter in the universe, one of the good approximation, and it's more than enough for our applications, is that the matter in the universe described as perfect fluids. Perfect fluids, it means that it's like we have a fluid, it's perfect, and we have 4 velocity vector for this fluid, and the energy momentum tensor for this fluid is given by this formula, T mu nu. Epsilon, or sometimes we give it the symbol rho, it's the energy density, B is the pressure, U mu is the 4 velocity for this perfect fluids, and here B is the pressure again. Usually we took that the speed, U, the speed of this 4 vector, it's taken to be on one axis, then 0, 0, 0 components. We can do, of course, this because that's if you have any velocity, and then you'll say, okay, I'll consider that this velocity, I'll take the x-axis along this velocity, and then the other components will be 0. Yes, we can do this. Then if we do this and we back to this equation here, and we apply that this is 1, 0, 0, and here of G mu nu, we know what's the component. Then we try to find what's the time components and spatial components of this one. So we'll find these non-zero components, T00, T11, T22, and T3. Now we can find the 0, 0, and 1, 1 components of Einstein equations, because we have here, for example, here, we have Einstein equations as R mu nu minus 1 over 2 G mu nu 8 pi G T mu nu. Then for 0, 0 components, we'll take the R0, 0. We have the expression for R0, 0. Minus 1 over 2 G0, 0. We have it's 1. Multiply by R. Now also we find what's the expression for Ricci scalar. This is the equation. And equals 8 pi G T00, and also we found what's T00 is. So this T00, the energy of the density. And if we combine them together, we'll find this equation. And if we took 1, 1 components of the equation, we'll find this equation. Now, of course, you will say, okay, now we have, we still have 2, 2, 3, 3 components. Actually, all the spatial components, they are identical. So if we try to derive 2, 2 components, we'll find it that's similar to this equation. and 3, 3 will be also similar to this equation. Of course, 2, 3, 3, 4, all of them, there will be 0. There is nothing. Okay. Now, what the benefit of these equations? This equation, look, give us the variation time of r and r dot dot and r. So we can, from this equation, in principle, we can find the expression for r as rt, where r is the scale factor. If we succeeded to find the scale factor, that will help us a lot. Why? Because now we know how we can describe the evolution of the universe. How the universe expanding, and how we can describe this expansion of the universe according to the substance in the universe, according to the matter in the universe. But the problem here is that, look how many variables we have. We have r, we have epsilon, and we have b. So we have 2 equations and 3 variables. Now, there is one of the equations also we can conclude it, which is the conservation of energy, where the conservation of energy, we can find it by taking that the covariant derivative of t mu nu, that will equal to 0. But actually, when we derive this one, we'll find this equation. We'll find third equation here. We'll find this equation. But unfortunately, this equation can be derived by these 2 equations. If you combine these 2 equations together, we can find this equation. So now we have 3 equations, but they are not independent on each other. We have only 2 independent equations. So we still have 2 equations, but with 3 unknown quantities or 3 variables. And as you know, that's if you want to be able to solve the equations, the number of the equations should equal to the number of the variables. How we can solve this one? We can solve this problem by identifying the components of the universe, because we know what's the matter in the universe. Mainly, we have the non-relativistic matter, the ordinary matter or baryonic matter. We have relativistic matter, which is represented by radiation, gamma ray, neutrino, and we have also the dark matter. Now let's focus on the ordinary matter and radiation. For ordinary matter, it's baryonic matter, so we know that it's pressureless. So pressureless means that there is no pressure. It seems like if you cancel one of the variables, now you have 2 equations with 2 variables. Usually we express this one in different way. We say that there is equation of state. This equation of states relate the density of energy with the pressure according to the type of the matter. So in case and the equation of states usually it's given like omega equals b over rho. So, or as b equals omega times rho. For the ordinary matter or non-relativistic matter, this omega equals 0 because the matter is pressureless. For radiation or relativistic matter, omega equals 1 over 3. So the pressure will be equals 1 over 3 times the density. For example, for cosmological constants, this omega equals -1, etc. So this is, by now we'll focus on these 2 types of matter, because we know that at the beginning to the universe, we have the radiation. We started by the radiation. Then as the temperature of the universe decreases, then we have the matter radiation equality, then we have the matter domination. So at the beginning, the radiation dominated on, or the universe was dominated by the radiation. Later, it was dominated by the ordinary or baryonic matter. Now, these days, we don't know what's whether the universe is dominated by the cosmological constant, by dark energy, or just as we mentioned in the first lecture, there is nothing like this. It's all what's happening. It's just that we need to modify the gravity as we are doing in FR theories of gravity. Anyway, so now by defining the equation of state between the pressure and the density, now we have, like if we have third equation, contains two variables. Now we have 1, 2, 3 equations with 3 variables, so we can solve them to find the expression for the scale factor. Okay. Now here, this is just deriving of Robertson local. Of course, I'm not going to read everything here. All what I need is just to take the things which we are concerned about it. So yes, now we have Fragment models. What's Fragment models? The first one is that's about the Fragment equations. We need now to write them in different ways. So just we can see them in a clearer way. So let's remember that this is the Fragment equations. This is the two equations of them. We found them by 0, 0, and 1, 1 components. Now here they suggest us to rewrite them in different way. So let's see, just here we have r dot dot. So just by arranging the terms in different way, we have r dot dot, and eliminating here r dot squared and substitute what's r dot squared from the first equation here. So we have this equation. That's r dot dot equals negative 4 pi g over 3 epsilon over 3b r over c squared. And now about the first equation, 376a, we can write it as this for the 3 possibilities of k. So it will take these forms. Now, this is about the equation of state. And let me check here because I read this long time ago. Actually, what I want to focus if that's about this. Okay, without reading here, we can see this clearly. What I care about is the following. Let's look at the first case. If we are talking about the non-relativistic matter, I focus on this one. In the non-relativistic matter, so B will be 0, and of course epsilon is larger than 0. It's positive. So here we don't have now this term, and what we have here is that r dot dot equals negative 4 pi g over 3 epsilon r. So now we can see clearly that this r here, r dot dot or a dot dot scale factor is negative 0. So there is expansion of the universe, but the acceleration of this expansion is negative. And this is what gives us in case of B. Now let's see what about if B equals 1 over 3 rho, the same idea. So here we have the same thing. This will still positive because the pressure is positive, and r dot dot will still be smaller than 0, negative. How we can fix this one? Actually, we can fix this one by only one way. If we assume that there is some kind of matter dominated on the universe, and this matter dominated, so we can neglect the radiation and the matter, and this matter should be the negative. The pressure of this matter should be negative, and at the same time, this B should be, in absolute value, should be larger than 1 over 3 rho. If we have like this matter, then that will be perfect, and we can assume that now we have here this accelerated expansion of the universe. But here I'm surprising about something. Yes, that's it. Yes. Okay, so this is the only case that we need matter, and this matter should have negative pressure. How we can find this matter? Actually, I'm sure that you heard about the big mistakes of Einstein about introducing the cosmological constant, so he can remain the static solution for the universe, not the expanding one. Now we can use this one. We can use this cosmological constant, and the cosmological constant the equation of state if that's P equals negative rho, because omega equals -1. And then we can recover this equation. 3b, so like if we have rho, it's the same as epsilon. I'm used to write it as rho, not as epsilon. And then yes, we can find it. We can find this accelerated solution for the universe. But as I said, it's not prefer this cosmological constant because until now we don't know what the nature of this one. Instead of that, we used the concept of the dark energy. It's a known form of energy, but satisfy the equation of state to have negative pressure and to make this A dot dot larger than 1. Until now, we don't have that unique model of or unique description of the dark energy. We have more than one model. There is many models that are succeeded to explain this accelerated expansion of the universe, but we don't have till the final answer about what is what is the correct description of this form of this dark energy. Is it quintessence, case sense, and what type of the potential of this, etc. Because we don't have observation about it. And of course, we have modified gravity. And this is one of the main goals of this series. That's by introducing the modification of the general relativity, we can get modified Friedman equation, and this modified Friedman equation can give us the accelerated expansion of the universe without needs to introduce cosmological constant or dark energy or whatever else. So this is the main point of these lectures. Now, let's go now to our lectures here, lecture notes, and to see what about the FR theories. What will happen if we use the FR theories? In the same manner of general relativity, and because of that, I introduce how we deal with the Friedman equations in case of general relativity. This is metric FR theories. Okay. This is about the FR theories. Again, this is the FRW metric, Friedman, Robertson, Walker metric, and this is for the perfect fluids. This is R, Ricci scalar, and now we have here Friedman equations or modified Friedman equations. How did we find these modified Friedman equations? Just go to Einstein or modified Einstein equations and take the 0, 0 components and 1, 1 components, and you can find it directly. It's not something difficult. It's really so easy to find it. It's not something you need to do it here. Because again, it's like that conclusion. And here, just take the 0, 0 component of T mu nu. Then for 1, 1, you'll find this equation. It's long equation, it's complicated, contains f prime, r, f double prime, r dot, r dot dot. Of course, we need to specify what kind of function we have here. So they wrote it in similar way of Friedman equation, like this. That's a dot over a squared plus k over a squared equals 1 over 3 kappa rho total. What this rho total, they took rho and the other terms where they are differ from the left side of Friedman equations, and they are not containing rho, of course contains f prime and r. They call it as density of curvature. The same thing for B of curvature. So it's just about arranging the equations again. Combining these two equations, we can find this equation. And now by this equation, we can see that we can succeed it and we can recover the case A dot dot if rho total plus 3b total will be less than 0. And now we have this possibility. Why? Because now rho total and b total contains rho and b for curvature. And especially about rho of curvature, it's nothing, that's nothing impose or force us to be positive, because it's related to the curvature. So for suitable function, for specific function, we may find it as negative, as negative. And this is about the condition to have this successfully negative here. So we can see that. So for the first side, that's now we have the possibility that the acceleration will be negative, will be positive. We have here negative. So if this term is positive, negative, then negative with negative, that will be positive. Again, this A here represents R in that reference A, the scale factor. And this is the equation of state for the curvature terms. It's B curvature over rho curvature. And this is, of course, we need omega to be negative. So we have B equals negative rho, something rho. Now, if we want to be like the cosmological constant and to recover the distal space-time, then omega curvature should equal to -1. And to have -1, then this equation should be satisfied like this. That's R3 over F double prime equal this. Achieve this equation. But of course, we are not forced to have the exact omega equals -1. All what we need just to be negative. And semi-distal, it's okay, not exactly as asymptotic distal space-time. Now here they are dealing with a specific case, because without specific F, all of this is our general talking. But now they took one of the models with R1 over R. So in addition to R, they add mu to the power 4 over R. They mentioned here that this is as a toy model just to discover what's happening here, because this model shows instability in matter sector. So here, let's stress out from the beginning that this is more toy model, because it has been shown that this model presents violent instability in the matter sector. In fact, there is no matter-dominated era, and there is a proposal to generalize this model and avoid some of the above problems was made in this reference. But now let's just introduce this model as a toy model. Now, if we look at the equation 61, let's see what's 61, what did they mean by this one? Yeah, this is a modified Einstein equations. But now instead of FR, let's go to the 61, but let's memorize which number this is, 37. So 61. So this is the equation. Oops. No. So this is the equation of 61. Let's go now to the page 37. Okay, so, and this is the equation here. So you see, all what's done here is just instead of F prime R, now we have R minus mu to the power 4 over R. This is and factor with dimensions suitable. So if we take the F prime R here, F prime R, that will be 1. And here you have mu to the power 4 over R, so that will be positive mu to the power 4 over R squared, R mu nu. Then we have here FR, so that's FR by the, let's see, oops. FR G mu nu, let's see what's happening here. I think here there is mistake. Let me check here. So that's F prime R, so it will be 1 minus, yes, that's correct. But here, if here R, there is no R here. Shouldn't be R here. So we need to cancel this R, because they just took, wait, wait, no. R, and here we should have R squared. R squared. If we want to take R out of this, should be R squared. Yes. Then we have here nabla mu, nabla nu. They entered the minus, so now the Laplacian will be the positive and nabla nu will be the negative. And you run 1 plus mu over 4 over R squared T mu nu over M blank squared. And yeah, this is the F prime R. So just only here we have R squared. We should have R squared. Or just as R minus, maybe this is the mistake that's here, should be R. Well, they were the same. So this is the equation now, equations of Einstein by taking this one, where reduced mass. Now the trace of this equation, if we took the trace of this equation, this is the trace of this equation actually. If we took the trace, and we introduced this one in the first lecture, how we can take the trace just by multiplying G mu nu, G mu nu, so here you have F prime R with R. So for this one, you have F prime R, R, wait, this one. Yeah, now look, multiply this one by G mu nu, that will be 4 with 2, so 2FR. So that will be 2FR. Now this with G mu nu, that will be F prime R, R, minus 2FR, and here we have a plus 3 Laplacian F prime R, because this G mu nu with this, G mu nu with this, that will be Laplacian, and G mu nu with this, that will be 4. So we have 1 minus 4, this is minus 3 with minus is plus, and here you have kappa T. Yes, so now we have 3 F prime, 3 Laplacian F prime R, and plus R F R minus 2FR equals, yes, so here also there is a mistake, that this should be F prime R, F prime R, and here we have, let me check here, 3 Laplacian F prime R, and F prime R, R, so here R, F prime R, so there is a prime. Now let's see that, let's remember that by from Einstein equations we found that if t equals 0, then R will equal 0, and this is that's maximal symmetric solution, Minkowski solution. But now let's see, what about if we have this case here? Then we have this here condition, that's, and if we are taking that c equals 0, this 0, and that's, we have R constant for now. Let's see if R constant, what will happen here. So if R constant, this term, we cancel this term. Then we have R F prime R. I'm confused about what this. Okay, now I understand. Now I understand what they did. Okay. Let's just see. They said that's okay. They wrote FR as R plus FR. So there is no mistake. Now FR, which is negative mu 4 over R. So when we have here, when I say that we have F prime R, it means that this one will be 1 This one will be here 1. So we have only f prime r because there is Laplacian. Laplacian 1, that will be cancelled. And here we have r f r. Yes, and here we have r f r. Why? Because we have here, let's see from this equation, that we have f prime r mu nu, so that will be r. Let me just so here I'm confused about this. Let me just rewrite it again. I didn't notice this one before when I prepared this lecture. You know, that's reading always is completely different from working on this the equation. So if we say that's fr equals r plus fr, then we have that's f prime r will equals 1 plus fr. So for this one, now we have 1 plus fr, and here multiply by r. Then we have from here negative 1 over 2 fr, but that should be negative 2 fr. Negative 2 fr, yes. And from here we have positive 2 positive 3 Laplacian fr. That will be equal to kappa t. Okay, so I can understand this term here. 3 Laplacian fr, yeah, this is the first term related to this term. So this term related to this term, it's okay. Now negative 2 fr, negative 2 fr, yeah, this one. But r fr, I think here no, it doesn't. It should be r. I mean here it should be r plus r fr. Should be like this. So we still have r missing here. We still have r missing. R if r, it's okay. But we still need r here. We still have r. Where is this r? You know, I was reviewing here what's written because I stopped the recording just to save your time, but I found that no, there is a mistake here in the just in the symbol. So all of this actually it's fr. So here fr, and here fr. So the only mistake that's here there is a prime, and where also there is a prime. And also there is prime here, r, f prime r. So here also there is a prime. How I conclude this? I conclude this as follows. Because look here, okay, now for the case, for the case of constant curvature vacuum solution, nabla mu r will be 0. So here we have r f prime r minus 2fr, and that's, look, we can see here that's r, and this is f prime r, and this is fr. So no, there is there is nothing like this. I expect that there is some kind of notation that they called the other terms as f big capital R and the first one f small r, but no, this is not the case. So now we have this equation here, and then this equation, if we want to solve this equation, we'll find that R will be positive or negative the square root of mu squared. And that's actually interesting because now we have distal or anti-distal of space. So we have distal space. So now we have that case of expanding. And if mu equals 0, we will recover the flat space and the FRW case. Okay, now if we look at this equation here, so this is the first node. Now if we're back to these equations of Fragment equation, so the time for the time components of the field equation, for this equation here, if we took the 0, components, we will find this equation here. For ij or 1, components of space components, we'll find this equation. Now if we put mu 0, what the meaning of mu 0, it means that here mu 0, so we have fr equals r. So if we put r mu equals 0, so that's all of this term will be cancelled. All of this term will be cancelled, and then we will recover Fragment equations again, but in terms of Hubble parameter. Hubble parameter, where Hubble parameter is a dot over a, the derivative of the scale factor, the time derivative of the scale factor over the scale factor. Okay, but now here what's written here. Look, now this equation is so difficult, it's so complicated to solve them analytically. It's so difficult doing that. So the new Fragment equations are the fourth order. You have here R22, where is it? H to the power 4. So it's too difficult to solve them because it's so difficult to solve it. So because of this, it's more convenient to transform the equation to Einstein frame. And now we can see what the benefit of Einstein frame. Remember how we converted the Einstein frame? That's we assume that g mu nu will equals to omega squared g omega minus 2 g mu nu tilde, and omega squared, we took omega squared as f prime r as fr, where fr here we'll take it as f prime r. And then we define the scalar field. You can review the lecture about the conformal transformation. Then we define that len omega equals phi. So len the square root of fr or f prime r will equal to phi. Then this omega square will equal, in terms of phi, exponential the square root of negative 2 over 3 phi over m Planck square. Maybe I made a mistake about the coefficients. You can review the second lecture easily. Of course, it's difficult. That's if every lecture and every step we can review everything. That would be so difficult. Will take a lot of time. But now, so now we have this omega squared in terms of phi, and we have this the conformal transformation for the time and for the scale factor. So the time in the conformal or Einstein in Einstein Einstein frame will take this form, and the scale factor will take this form. And this is actually happens because of the idea that ds in the Einstein frame should be equal to ds in Jordan frame. But this one will be, you know, that c squared d tau squared plus g mu nu dx mu tilde dx mu tilde. While here that will be dt squared plus oh, I'm sorry, here also there is g mu nu. Let's say g mu nu, you know, I wrote it in incorrect way. So this is g mu nu tilde dx mu tilde dx mu tilde. And here we have g mu nu dx mu dx mu. So if we define the variation with this one, it's I think omega minus 2 g mu nu, and compare between this and this, we can find this transformation for the time. And remember that's omega squared, we defined it as f phi. So this is for the time, and this is for the scale factor. Then we can define the Hubble parameters in Einstein frame as a tilde prime over a tilde, where prime now is the derivative with respect to the dt tilde. Then what we are trying to write here, to write h tilde in terms of h in Hubble's parameter in Einstein frames, in terms of Hubble parameters in Jordan frame. So h tilde, let me just do this one quickly. That's it's a prime, a tilde prime over a prime. So that will be for a prime, it's a the square root of f. Now about the derivative of this one, that will be d over dt tilde of a tilde, but we need to relate it to the original a. So here I write it that's as a square root of f. Now we have 1 over a the square root of f. Here we have a prime the square root of f plus a multiplied by the square root of, this is 1 over square root, this is the derivative of this one. And here of course there is f prime. But again, we don't need a to be the derivative with respect to t tau with t tilde. We need it for the ordinary or for the original time. Why? Because we need to relate h tilde with h. So this is d a prime is d over d t tilde of a. So let's take it as d over d t as d tilde as dt over dt tilde times d over dt. Then here we'll have 1 over the square root of a square root of f a prime. Now we have that it will be a dot, the derivative with respect dA over dt. By in addition, we have dt over dt tilde and dt over dt tilde, that will be the square root of f. And you have already the square root of f, so now it seems like you have f. I hope that I didn't make a mistake. I'm sorry, you have the square root of f, and you have 1 over, I'm sorry here, because we need dt over dt tilde, so that's 1 over square root of f, 1 over the square root of f. So here now we have a dot, the square root of f, already you have the square root of f, over the square root of f, because we change from the derivative with respect to t tilde to t. And here we have a f prime over the square root of f. Then we have this here, a dot, the square root of 12, and then we have this one. Now, a dot a, this is h of the square root of f. But now here, let's see what we have here. That we have here, that's a multiplied by a, that would be cancelled. So now we have 1 over f, because the square root of f with the square root of f, 1 over 2f. Then here they wrote f, and in terms of phi, in terms of the square, in terms of the scalar field. Why we did that? Because now phi f is given as exponential of phi with some coefficient. So f prime will given also as exponential phi with phi prime. So now we have here f, and here we have f prime. So the exponential with exponential in the denominator, that will be cancel out each other. So the result that we'll have f prime, and of course the coefficient which is coming from here, the square root of 2 over 3, and etc. So now this is I'm sorry if I'm explaining this fast, fastly, because you know that if I want to conclude everything, that will take a long time, and I'm afraid to be boring lecture, because I know that anyone will care about this one and will give attention to like this lecture. Of course, he should be some kind familiar with the general relativity and familiar with these derivations. So I don't think that we need to go to step by step. And by the way, when I date sometimes some steps because I confuse about something. Honestly, I didn't prepare this one before. I read it, but I didn't do all the calculations. So when I did some calculations, because it seems for me it's not clear. Because here actually I confused about how did we get this one. So I found that okay, let's try to conclude it and to find. So this is the relation between the Hubble parameter in Einstein frame and the Hubble parameter in Jordan frame. Okay, so where prime denotes the differentiation with respect to the conformal time, and here we mean by the conformal time the time in Einstein frame. Now the scalar potential defined in 124. Let's just review what's 124 and this is 39. Yeah, this is 124. Take screenshot just to check the equation. And here 39. Okay, so let's check that this is. So now here we have RFR, so minus R, FR squared. So this is F, yes, we already about this. And now about this R, FR minus F, let's remember that F is 1 plus F. And here we have R times F. So that will be like the square root of F minus 1. How did we get this? I'm still confusing about what they mean by F, capital F and small f. For that equation, it seems that it's only just mistake and typo mistake, F, capital F and small f for this one. But now it seems that there is meaning here of this one. Because here they use like F, like if F is, you see, like if F is only the derivative of F prime. So here it seems that they mentioned F capital as F prime. So if we use this assumption, this notation here, let's see what this meaning. That's it mean that this will be 1 minus mu to the power 4 over, and this is plus, over r squared, and here you have minus. So like if they say that's okay, this is mu squared over r, and here is squared. But let's see if this equation give us this r if r minus if r if r minus f. So let's see if we say that if this is f and fr is just as 1 plus mu to the power 4 of r squared. So this is, now I'm trying to see what will happen if f is the derivative of fr, if we can cover this equation, minus f, where f is r, here r, minus mu to the power 4 over r. So let's see. So that will be r, and here r, that will be cancelled. So this, and then we have mu to the power 4 r, if r. So we have mu to the power 4 over r plus mu to the power 4 over r, and here we have r squared. I think we have 2 also. Yes, we have 2. Yes, and R with multiply by this, so now here we have over R. Yes, like this. Then we have, this is will be mu to the power 4 over 2R. Yes, and this is yes. Over 2, but why we have here over 2 here? We don't have over 2 here. Because already we have here 2. Yes, now we can. It's easy. Now it's clear. So now I work on this one just to be checked. That's now F represent F prime phi. Okay, now it's okay. So F capital, it's F prime phi. F capital phi is F prime phi. It's not, if we say that's F phi is R minus mu to the power 4 over R, then F capital R, it's not only this part, no, it's 1 plus mu to the power 4 over 2R squared. So this. Now if we apply this formula, we can find that that's yes. V phi will be given by this. Now here they say that let's know that that the scalar field potential is 0. The scalar both when the scalar field itself is 0, or when this goes to infinity. The potential achieves its maximum value at the point where dV over dF equals 0, i.e. F equals 4 over 3. Okay, that's clear. Now here it's also convenient to define Einstein framed matter energy momentum tensor defined by this. And now we have here that mu will be 1 over F mu, and of course why? Because there's derivative with respect to the time. So if you want to convert from the frame in Jordan to frame, so that will exist omega down, and omega is the square root of F. And for rho, that will be like this, and B will be like this. Now, if we want to follow Y rho, it's given by this, and B is given by this, we can back to Faraoni book that's about scalar geometry here. What is it? Yes, here. You can review this book that will be written in details. But for me, for now, you know, that's the scalar tensor theories in scalar tensor theories, or cosmology in scalar tensor theories by Valeriano Faraoni. But for now, even me, I'm not remembering quickly how we can find that rho is given by this and P is given by this, but it's easy to find. Then the cosmological equation of motion in Einstein frame is given by this. Then we find it that is given by this. How? Just by taking, now you have this here, and we have the modified equations is in Einstein is written in terms of scalar tensor. So all what we need just to back to these equations. Let me show you the equations. Yeah, this one, this equation. I'm sorry, not this one. What is this? See, that's it's not written here. I think it's not written. Anyway, so we have now this equation here. So if we took the variation with respect to g mu nu, we can find the modified equations of Einstein. Then taking the 0, 0 components and y and the ij components, we can recover where okay, so then we can find the modified Einstein equations and substitute. Yeah. You know, now after giving this lecture, I'm really confused whether this method is suitable or not. Usually I don't like, to be honest, even when I see lecture and someone he just read from the book, I feel that's no, this is not interesting. Usually I prefer something is written by hand, but honestly because this will take a long time, so long time. So let me finish this lecture as this, and then I will think, and I'll see if it's better to conclude it by hand and using the blackboard. I'll see, maybe I will record 2 lectures. I cannot see that I can cover all of these topics in 1 lecture. Okay. So where we have been. So now this is the engine. Now we can see that they are so clear and they are so, you know, that we avoid the 4 order and all of this complication in case of by working in Einstein frame. So they are talking here about the Laplacian of the phi and how we can find it, something all of them in analytical. But here what's important. Let's now make some comments about the solution of 242 and 243. These 2 equations. The first one, it's more easy to find vacuum cosmological solution for rho equals b equals 0. The beginning of the universe corresponds to r is infinity and phi equals 0. Depending on what initial conditions we specify phi and phi prime, there are 3 qualitatively different solutions according to solve these equations. Let's see. A eternal disturbance is obtained when the scalar field comes to the rest after reaching the maximum of the potential V phi in equation 239. This is 239. This state is obtained for critical value of the initial condition, namely phi I prime equals phi C prime, when the universe evolves asymptotically to Disturbed solution with which turns out to be very unstable because any perturbation of the field will make it roll away from the maximum and of its potential. So this, the first situation, is unstable. Second, Bohr law accelerating, i.e. achieved phi I prime larger than phi C prime when the field overshoots the maximum of Vf, and the potential can be further exponential like this. And in this case, it's easily to solve a tilde t tilde over t to the power 4 over 3 tilde, which corresponds to EA t squared. Thus, the universe evolved late time Bohr law inflation. Future singularity, it's obtained when phi I star prime less than phi prime C, case in which scalar field rolls back down to phi equals 0. So, and because of that, they mentioned that this model, it's as considered as toy model just for practicing, or take a look about this one. It solved the idea for the late accelerating of the universe, but it gives us unstable solution. So at the end, it's an acceptable one. Okay. Now here we have R squared cosmology, the most representative model of R squared. It's called Starobinsky model, with the help of which inflation can be explained without need of scalar field. this model is obtained for. And actually, most of the works in the field of R squared, this model will be in the field of inflation, because it seems that it's introduced at the beginning to solve the inflation and to explain the early accelerated expansion of the universe, where alpha here is constant, and we have this is Einstein equations for this, and we have modified Fragment equation, but now we have them in Jordan frame. Because that's now it's easy to solve them, no need for to move to Einstein frame. So, and the answer will be that H dot will be like this, and H will be like this, and this is A. We can see that A is exponential with the time. It means that A dot dot will be larger than 1. And here they are working on Einstein frame. And that's it. Yes, that's it. I will stop here for today, and I promise that I will think, if I found that it's better to repeat this lecture and divide it into 2 lectures and doing all the calculations by hand, because the point of this lecture is not to give something, something fast, because, as when I was a master's student, you found many lectures about general relativity as introduction. You can find many lectures about modified gravity. But that in 4 lectures, they will cover FR theories and scalar tensor theories and vector scalar tensor theories and the Palatini formalism. So there is no details inside it. I know that as graduate students and master students, you need something to be done in details to see how we can do this. This is the first time we're introducing something like this, and I know that's not all the university give the required curriculums to cover all of these topics. And this is actually the goal behind this series, to help the others to give something in details about something advanced, something it's not exist on the internet, and that will help to create some kind of scientific discussion, scientific community in the field of cosmology and gravity. Thank you for your listening. I really appreciate if you reach to the end of this lecture, I really appreciate that. And I appreciate it actually because something personal, but I appreciate that because this means that you are theoretical physicist. If you cannot be patient to the end of a lecture, you are not theoretical physicist. I know that's for most of the people. These topics, this reading, this symbol, they are so boring, they are something complicated, they are something, most of the people don't like it. But if you are theoretical physicist, you should like these things without any improving, without any show. Like this, as theoretical physicists, we like these symbols. Immediately when I say new, when I say like these symbols, I feel so interesting. I'll be so excited to follow the things and to follow the lecture. So thank you for your listening if you reached to this point. And have a nice day, and see you next time in another lecture. Oops. And now I forget to make share for the screen. Oh my God. Oh my God. So most of the explanation now, I hope that I didn't forget sharing the screen from the beginning. Okay, that means that I'm forced to repeat this lecture again.